In this video, I will explain you what is meter bridge. So meter bridge is simply application of Wheatstone bridge. Now whatever the principle, whatever the equations we have learned in Wheatstone bridge can be applied in the case of meter bridge because this works on the principle of Wheatstone bridge. Okay. Now, so the use of meter bridge is nothing but to find the value of unknown resistance. Now you have an R unknown here, unknown resistance, and you are having a non-resistance and a resistive wire having 1 meter length. So first I'll give you the introduction of elements in meter bridge. So you are having a conductor here, that's a brass conductor. So whenever I say conductor, you have to take the resistance of that as 0. So this is a brass conductor, again a brass conductor, again a brass conductor. So resistance of all these conductors are 0. Now unknown resistance here and non-resistance here, and the total value, this is also a resistance. So the red colored one are resistance. This is resistance wire having 100 centimeter or exactly 1 meter length. Now this wire has a property that if you are taking 1 centimeter part anywhere and measuring the resistance, that will be the same. So basically it's uniform cross-sectional area across the wire. So resistance per unit length is the same. So the total resistance, if it is R, what is the total length? 100 centimeters. Now this is resistance per unit length, that is unit centimeter. And let's say I can take it as rho. Rho is not resistivity, it's a constant, that is resistance per unit length. Now what will be the resistance, for example, of length L1? Then that will be L1 into resistance per unit length, that is R by 100 centimeters, where L1 is measured in centimeters. Anyway, come back to this. Now we have an unknown resistance and a non-resistance. How we will get the value of non-resistance? By connecting with resistance box here. Now resistance box is a connection like this. So we have a brass element here, another brass element, another brass element, another brass element. In between the brass element you have 5 ohm. It can be any value, it will be given in the resistance box, you will see in the lab. So like 5 ohm, 3 ohm and 1 ohm. Now we will be inserting the keys to get a desired value of resistance. For example, when I am inserting a key here, now when we are connecting one end of the battery here and another end of the battery here, what will happen? The current will pass. Current will come here to the brass. It has two paths here. One is high resistive path, other one is low resistive path. So current will go through here. It will miss 5 ohm. Then these two things are open. Okay, so when it is open, then it has no path in this way. It has to go through 3 ohm and 1 ohm. So what is the total resistance here? 3 plus 1, 4. Now let's say when we are going to insert one more key. So what will happen? Current will pass through this and even pass through this and also pass through this, because these are high resistive path. These are brass elements, low resistive path. So current will choose this path. And here can it go? No, because the key is not inserted. So it will go through 1 ohm. Anyway, this is just an additional information. Thing is, with resistance box, you can get different value of resistance. That's all. Okay. Now, see, this is a Wheatstone bridge. Like to one terminal, I have connected one resistance. And let's say this is 1 meter length. Okay. So if L1 is a portion, then what is remaining portion? That is 100 minus L1. 100 minus L1. So L1 is a measured centimeter, measured distance. As the total distance or total length is 100 centimeters, the remaining part will measure 100 minus L1. Now, at L1, what is the resistance? L1 into rho, where rho is nothing but resistance per unit centimeter. So, let's say when we are making a connection in this way, L1 into rho will be this resistance. See, it's 1 point now. Now from this point, we have a galvanometer connection and one end of R2, that is non-resistance R2. Now R2 is connected to point B let's say this is point A. Now 100 minus L1 is also connected to point B, and one end is at here, this point where L1 ends. So from L1 ends, we have another resistance, that is 100 minus L1 into rho. Okay. Now these two, this one and this one is connected to the same point. Now from galvanometer, the connection comes in between R3 and R4. What is R3? L1 into rho, and R4 is simply 100 minus L1 into rho. So comes here. So it's a Wheatstone bridge that we have concluded, but it's not a balanced Wheatstone bridge. That we can say only when galvanometer deflection is null, that is 0. So we will keep galvanometer here. Now R3 is less. Okay, now when we are moving galvanometer to this side, so that more length will be there for R3. R3 will be measured in between A and till the galvanometer slide. Now R3, when galvanometer I am keeping here, this is R3. When I am keeping here, this one is R3. When I am keeping here, this one is R3. Now R3 is this one. Let's say, for example, what is R4? Then the resistance of remaining portion is R4. Let's say we have slide this galvanometer and we have founded the null deflection. Null deflection means galvanometer gives a zero deflection or current passing through, that is 0. Let's say that has happened at the length of L1. For example, at L1 this has happened. Now what is R3 here? This one, L1 into rho. Now what will be R4 here? R4 will be 100 minus L1 into rho. What is rho? Resistance per unit length. Now per unit length, if it is rho, in L1 length, that will be rho into L1. With 100 minus L1 length, that will be 100 minus L1 into rho. So this one is L1 into rho, 100 minus L1 into rho. Galvanometer gives null deflection. So this is a balanced Wheatstone bridge. I can apply the principle here, right? Yes. That is R1 divided by R2. So this one is unknown resistance divided by known resistance is equal to L1 into rho divided by 100 minus L1 into rho. Where I can cancel these two, rho and rho. And R1 is unknown resistance. So R unknown is equal to R2 into L1 divided by 100 minus L1. This is very important relation, and this is how you are going to get the value of unknown resistance. Now, so in the lab, what you are going to measure? You are going to measure R2. R2 is known resistance and L1. So with using rheostat, you will be changing the value of R2 into different value. So 1, 2, 3, 4. You are going to change R2 with 4 different values. At that time, you will get 4 different null deflection points. So you are going to measure the value of L1 first time. L2 with 2 you will get different value of L2. With 3 you will get different value of L1 it is 3. With 4 ohm R2 you will get a different value of balancing length. So all these things are 3 different points. These are 3 different resistance. So this is R2, first R2, second R2, third R2, fourth R2. So let's say 100, 200, 300, 400. Accordingly, we will get balancing length. Now from these you can get the value of 100 minus L1. 100 minus L1. Now you got L1, 100 minus L1, you have R2. Now we will substitute in the equation. R unknown is equal to R2 into L1 divided by 100 minus L1. So you will get different values of R2. But the thing is, these values have to be same. So for example, if this is 100 here, you may get 99 here, you may get 98.5 here, 100.5 here. Now how to get the accurate value? Take more measurements and find the average, and that will be the accurate value. So find the average of R unknown average so that we can eliminate maximum amount of errors. The final value will be more towards accurate value. Thank you.